Hello everyone. In this video we're going to talk about generative adversarial networks or GANs, which are quite a bit interesting, and this idea was introduced in 2014 by Ian Goodfellow, and these are quite popular networks, okay, because of generating I would say fake images, probably, huh? That's the most thing you heard about them. So let's talk about it. So if you remember in my machine learning videos, one of the things I talked about was random forest, where you have a bunch of decision trees working in parallel and in synergy together to make a better decision, right? Yeah. So sometimes we use units of machine learning or deep learning to work together to achieve better results. Sometimes we have them in competition, and this is the idea of these adversarial networks. We have two networks in competition, in adversary. Each one is working against the other one, and by competition between these two, we try to get better results, and that is the brilliant idea of adversarial networks. So like what? For instance, we have two networks here. One of them is called generator, which is trying to create fake images from some real training or authentic images, right? So we give it some training images, like for instance here, the MNIST data, and say, hey, make pictures like these, but not exactly these original ones, very similar to them that a normal human being without a ton of training might not distinguish between them. So this generator network will start from scratch, basically. We'll see it starts from basically noise and try to generate pictures that are very similar to MNIST, something like this, generate some fake images and make them closer and closer to the real ones. And there is another network parallel to it called the discriminator network, which is basically a binary classifier, which if you give it real images and these fake images, it will tell you whether these images are fake or real. And the job of training is to make each one of these two networks better at what they're doing. So make this generator create better and better fake images, closer and closer to the real ones, and this discriminator to be able to distinguish between really good fake ones and the authentic original ones. Okay, so they work against each other, and they keep each other in check, basically. Right? And they try to improve at the same time, and this training will keep on going until this discriminator basically can no longer distinguish between fake and real images and gives up. Say, hey, you're now too good. This fake image, this fake picture that you make, I can barely distinguish, right? And so you have seen this GANs probably on the web, that they made pictures of people that are not real, right? They make pictures of people who do not exist in the real world, and they are very good at it. Let me show you some samples. Okay, so take a look here. These are some of these pictures, right? Look at that. This person does not exist, or these people all in this picture, they do not actually exist. These are all made by these GANs. Imagine that. Imagine how powerful this is that can make this perfect, realistic images of people. Okay, so these GANs are really something, and they are really brilliant. Now, how do they work? As I said, we have two networks that are working at the same time simultaneously. One is called the generator, which tries to create new data, basically starting from noise, from scratch, and make them as close as possible to the training data, and the discriminator that is doing, as I said, the binary classification, saying whether they are fake or not. And they get better and better until the discriminator can no longer distinguish. So it's something like this. For instance, let's say I want, these are my training, this is my training image. Of course, you don't start with one image, you typically have a ton of images, but let's say I want to generate a fake version of this image, which is my channel logo, right? So what do? I pass it to the generator, and generator starts from noise. So in the beginning, this is what the generator has at the beginning of the update. And so discriminator compares this fake image against this original one. Say, hey, these two have nothing in common. So it says, no, this is fake. Then the generator tries to move these pixels around and change their intensities and come up with what? Come up with something that is closer to the training image. So now in the middle of training, you might get something like this guy in the middle, which is similar to that, but of course it's missing a ton of features. Still, discriminator is able to say, hey, not good enough, I can easily detect, it's not right. And at the end of the update, you might end up with something like this, which is very similar to the original one and is too good now the discriminator can fail to detect. And the differences might be very, very small. I mean, like if you look, the differences is like this region, right? You see here, these two, right? They don't exist in the original image, right? These two features, they do not exist here. Or for instance, if you look again, if you look at the nose here, the tip of the nose has a straight portion, but here it's just a sharp point, okay? So very, very similar, right? And these two, even with a naked eye, it might be very hard for anybody to distinguish. Okay, at this point, discriminator said, hey, you're good, I cannot detect anything, any fake, and we stop right here. So it generates this fake version of the original one for us. Now, what kind of cost functions do we use for the discriminator network and for what? For the generator network. Discriminator is easy. It's doing a binary classification. So binary cross entropy is, of course, what? The appropriate loss function. And we can train it with that. What about the generator? The generator goal, remember, one more time, is to what? Is to fool the discriminator to say all that it has created are real images, okay? So if we say for the fake class of images, the output should be 0 out of discriminator, and for the real ones, it outputs 1. The goal of training the generator is what? Is to force the discriminator so all of its outputs are equal to what? For 1, even though we know it's fake outputs out of the generator. So the goal, again, goal of training the generator is to force the discriminator to say all of them are true. Now, how do you do that? Well, since you're updating the generator weights, at this point, you have to freeze all of the weights of the discriminator, okay? And then what kind of target would you use for the binary cross entropy? Because remember, at the end, these outputs are coming out of discriminator. So I should, even for training the generator, I should still use the binary cross entropy. Because I'm not directly taking the output of the generator, right? And comparing them against something, I'm taking the outputs of the whole network, which is the discriminator at the end, and basically calculating, using those for calculation of the loss function. So I still use the same function, but as I said, we want all of the targets to be what? To be 1, to be all true images. So what happens is, this is your cross entropy, binary cross entropy function, which you use for training the discriminator. Now, when it comes to training the generator, here y's are the target data and y has are the predicted data. Here, since we want all the y's to be 1, if for yi you plug in 1, this guy will go to 0, this one becomes 1, so you simply get negative 1 over n summation I from 1 to n of logarithm of y hat I. So this is going to be the cost function that you use to train what? The generator. The left one is the one that is for the discriminator. Okay? Now, one other thing we have to talk about is how do you create fake images from noise? That's probably one of the hard parts. How do you go from here to here to here, right? If you start just from scratch with noise, how would you convert them to something close to the training images? So, first of all, what kind of noise? This noise is going to be a vector, a multi-dimensional vector, And it comes from what kind of distribution? It comes from a Gaussian distribution. So it's a multi-dimensional Gaussian distribution vector. That's what this noise is. And then what's the dimension of this? The dimension of that is clearly lower than the dimension of the image, right? So if we go back to the MNIST data, remember these MNIST data, they are 28 by 28 pixels. So if we want to look at the dimension of this, this is like a 784 dimensional space, okay? Now the goal is to reduce the size, reduce the dimension, go to a lower dimension space, which, by the way, there is a name for that. We call the latent space. And here, so we definitely need to choose a number for the size of this vector that is less than 784. What number? That is a hyperparameter that you choose. That's the dimension of this latent space, okay? So you can try different numbers, and you'll see when I go to the TensorFlow code, I'll show you. But that is a number that you choose, okay? So you start from this lower dimensional space. You create a vector from the Gaussian distribution, and then what? And then you try to move toward the image, right? Because in the beginning, you don't have a fake image. In the beginning, you only have what? A vector with so many variables. How would you, first of all, convert it into something by something image, right? 28 by 28, 64 by 64, right? So this picture here comes from the original paper on the GANs. But if you see here, the way that you do it is by a combination of projection and what? Reshaping. So you see this vector is first converted to a long matrix, which is a small number of rows and columns, but the third dimension is long, like 1024. Then it is reshaped into 8 by 8. Now the depth is reduced to 512, to 256, to 128, and the size of the matrix is getting bigger and bigger until ultimately you go down to a 64 by 64 and only 3 channels, which are red, green, and blue. Okay, so the way that you do it is by basically, I would call the opposite of what you did in a convolution neural network. Remember, in convolution neural network, you started with an image, and then what? You basically applied a filter, not just one, a bunch of them, and you created what? You created a bunch of features. Remember that? And then you moved on, and each time you reduced the size of these convolved images, but instead you increase the number of them, right? Which is exactly this one. If you look, this one here, if you break it down into slices, this is a bunch of smaller slices, 8 by 8, but you have more of them, 512 as compared to 256. Right here, the sizes of them are bigger, but you have fewer slices, right? So you see, if you look at this, this is the exact, and at the end, if you remember, we did a global max pooling and we converted into a 1 by n vector, right? So this was the global max pooling. And we convert it into a vector that we can pass to our dense layer. So this one is exactly the opposite. We are doing the exact opposite of that. And what we do here is upsampling instead of downsampling. We did back then in CNNs, we used a pooling layer. Here we use an upsampling, basically. And by that, we can convert our vector back into an image. So if you look at a typical generator network, which again, this is coming from the paper, you see they added a dense layer, right? And then they added a, for the cost function of that, they added this is another difference we have here. You add a leaky ReLU, okay? And with alpha of 0.01, if you remember from one of my previous videos when I talked about cost functions, or sorry, the activation functions in deep learning, one of them was leaky ReLU, which on the negative values, it doesn't generate zero. It generates basically some kind of line where the slope of that line is a parameter under your control. Here is 0.01, okay, which is a typical number for a leaky ReLU. And then again, you see here we are adding more dense layer. So here we are upsampling. For activation, we use tangent hyperbolic next, and finally we use a reshape to reshape all of those several feature map planes or matrices into one giant matrix. So here we need to use reshape layers and dense layers, and as I said, one of the activation functions which is used is leaky ReLU as opposed to what? ReLU. And you might say why? Because in this process, if we encounter negative numbers, we don't want to the output of the layer to be zero for them. We want still to generate some numbers, okay? So this leaky ReLU is used more. One more thing I need to say is this latent space, which is the low dimensional space, we assume that this is a lower space that captures the underlying structures of the image. So remember when you do PCA, right, principal component analysis, you bring down an image to a lower dimension space that captures the major structures, the major variations in the image. And that's something you're doing here, right? And this latent space is something like what you did in PCA. And by the way, in my next video, you're going to see me talking about autoencoders, which is basically doing something similar to PCA. And in that autoencoder video, again, I come back and I talk about this latent space. So this is the lower dimensional space that basically contains all the major information in your picture. And the dimension of that is under your control. If you choose it very small, you're probably not going to be obtaining all the major information and structure in the picture. And if you go too high, then you have not done a very great job in dimensionality reduction. So now one more thing before we go to the TensorFlow code is a loss function. If you plot the loss function, I'll show you in a second, the loss function of training for a GAN is not going to be that nice, smooth, monotonically decreasing function for both the training and the test data. They are not going to go like that. Why? Because it's not a single network that you have here. It's two opposing networks. Each one is trying to work against the other one. And so here, if you look at the training and the result of training, which is the loss function per epoch, you see it goes down, but then you see a ton of oscillations, as you see here for both the generator and the discriminator networks, okay? So do not expect this kind of perfect, smooth, monotonically decreasing behavior all the way. Again, it drops, but after a while you see these oscillations start, because each one is trying to cancel the effect of the other one, and so you get these oscillations. That's one of the other things you need to know. So now let's take a look at the GAN code here, which we're going to do on MNIST. So we're going to use Adam optimizer. The layers we need is dense, input, dropout, batch normalization, and leaky ReLU. So the first thing we do is we get the data of MNIST, and we get our X and Y train, X and Y test. One other thing we do is this data in these pictures are from 0 to 255. So instead we subtract half of 255, which is 127.5. We subtract all the pixels, this number, and then divide it by that number. So this way your pixels me add that. Pixels go from the range 0 to 255 to negative. Basically, if you divide by this number, this becomes negative 127. This becomes 127. When you divide, it goes from negative 1 to what? To 1. So here we center our pixels around 0. This is more useful for training your neural network, as we have seen in the past. We want to center it around 0. The next thing is we need to know the dimensions of the training and the test data. So here, the dimensions of the pictures, N, W, and H. If we go and look at them, let's see if I have them here, or seems like I ran this quite a while ago. So if I just show you those, you see that here MNIST is just like what I described in one of the previous videos. The images are all 28 by 28. And there are 60,000 of them, 50,000 for training, 10,000 for what? For testing. Now here, the dimension that I choose for that latent space is 100, which is clearly what? Clearly less than 28 times 28, which was 784. So you have to do some significant dimension reduction. Again, if it's very small, like 2.5 or so, you cannot capture all the structures. And if it's very close to this 784, like 500-600, then you have not done a very great job, okay? So you want to have something like an order of magnitude or so smaller. So here we go with 100. And now we need to build both the generator and the discriminator networks. In TensorFlow, there is no single layer called generator or discriminator. You have to manually add those, create those by a combination of some basic layers that you have. So here, look, I create a function called build generator, and all you need to pass to it is that latent dimension. So what does it do? It first takes the input from an input layer where the shape is latent dimension by 1 basically, and 1 you don't show it. Then you pass it to what? To a dense layer of 256 with a leaky ReLU alpha of 0.2 activation function. Then you jump to 512, then you jump to 1024, and finally you go with the dense layer with dimension D. Now what is this D here? If you see, this D is H times W. So that is what? That's basically 784. That's the height times the width. And now if you look, in between these dense layers, we use the Bash normalization layers with some momentum to improve the performance of the network. And finally, we say that the model is with I and X, where I is the input and X is what? The output to the model. And what does this function return? It returns the model. So it takes that dimension 100 and it returns a TensorFlow model that you can train. One other type of network that you might see used in generator networks is what we call the convolution layer, right? So remember here we did the opposite job of convolution, right? When we went from this vector to the image. So that you might call the convolution. And if you look at the TensorFlow documents for deep GANs, you can see here when they made this generator function, you see we have here the dense layer Bash normalization with leaky ReLU, and here we have a reshape, and then this is that layer I talked about. It's called conv2D transpose. This is a layer that does deconvolution. So you can use this kind of layer for it as well. And here you see that the generator layer is made with a lot more. The generator network is made with a lot more layers than the code I have over here. There are a lot more dense layers, there are reshape layers, there are deconvolution layers, and so on. So this is a simpler network compared to what you see here in this documentation. Feel free to use this part here. Remember the types of the layers that you use and all of these hyperparameters, the number of neurons, these are all under your control. And then for discriminator, what you need is to give it the size of the image, and then you get the input with that size of the image. Then you need to bring that size of the image down ultimately to a single number, which is a fake or a real, which is a 0 or 1. It's a binary classification. So at the end of these dense layers, you need the dense layer with 1 neuron, and the activation of that has to be sigmoid. The previous ones, which are kind of reducing the dimension, and you can use convolution networks for these if you want. Instead of a dense layer, you can use convolutions, but this is more common, using a dense layer with a leaky ReLU, and bring down the dimension ultimately to a 1, which is an output, fake or real. And you see again, it returns a model. So now I have these two functions that generate the networks for me. So now it's time to combine them into one combined model, which is the two of them together, compile it, add the loss functions, and train. So you see here, I call this function, I pass to it the size of the image, D, which is rows times columns, H times W. It knows that it's 784, so it makes the discriminator network. And to compile that, we say the loss function is binary cross entropy. We use Adam optimizer with 2/10,000 of learning rate and 0.5 of momentum. The metric is accuracy. For generator, again, we call the build generator function. We pass to it the latent dimension of 100 that we chose. And then here we need to combine them. Now, if you remember, the way that we combine is what? We have to start. This is my entire network here that you can see in this picture. This is my entire network, where this is the output of the network and this noise is the input of the network. Okay? So this is the input again to the combined model, and this is what? The output. So how do I go about it? So first I need to create a variable that represents the noise. I have to pass the noise to the generator. It gives me a fake image. I pass the fake image to the discriminator, and then the output of that discriminator is the output of my combined model. And I have to pay attention that when my goal is to train this generator network, as I said, we have to what? We have to freeze. We have to freeze what? The weights of the discriminator network, so only the generator network can be trained, right? So if we go back here, you see here I made a variable z, which is an input layer, and the shape of that is latent dimension. So that is your 100 by 1 vector of random noise. This represents your multi-dimensional noise. I pass that to the generator, so it gives me this fake image. And then what? I pass that fake image to the discriminator, so it gives me a prediction of whether it's fake or not. And then that output fake prediction and the input z, if I pass them to the model, this is my combined model. The loss function for that is again binary cross entropy. I use the same optimizer. The only thing I did here in the middle is, because this part is for generator network, I made sure that the discriminator trainable for this part is what? False. Now I go ahead and start the training. I do it in batches. The batch size is every 32 images, and I use a large number of epochs here. You need that to get good results, so 30,000. And this sample period 200, I'll tell you what it is. Okay, this is just a number for displaying the results. So this is not a really major parameter. The major parameters are these two. So the next thing we do is I want to store the results of these generator and discriminator loss functions, so later I can plot them. So I start them with empty, and then I keep appending to them and adding to them. What is this 0 and 1? I'll tell you. But so here, I cannot use the function fit. I need to use a for loop to train my network. So I need to store these values in the D losses and G losses. I cannot just go to my model dot history of losses and just get those results and plot it, because here we do the model is not a simple sequential model, and again, we don't use the dot fit. We don't use that dot fit. Here we do the training per batches in a major in a major for loop that you can see down here. And since we do it per batch, the training is done using train on batch for the discriminator, and then train on batch with zeros. I'll tell you what this one is. And then we also have train on batch, but we do it on combined model. But for the combined model, remember, we here ask the discriminator to not be trainable. So when we get this G loss out of the combined model train on batch, that's just the G loss, because the discriminator weights are frozen for this step. For this step, they are not. When we are training, they are available for update, but not in this other step. So going back to the rest of the code, one thing is here I need to store all of the, I need to also store images. What kind of images? These intermediate images here. These ones. I need to store these intermediate images also in a folder. So I go ahead and create a folder, and I store all of these intermediate images into a folder. Now, would I use all of them? Because here I have 30,000 epochs. So would I store 30,000 images? No. I only just basically store a subsample of them. How many? Basically every 200. That's this number. So every 200 epochs that it goes forward, I go ahead and basically store the intermediate image. Okay, that's what this 200 number is for. So first thing I say, if this folder does not exist, and for here I need the operating system. If operating system path exists, GAN images does not exist, go ahead and make DIRs. Go ahead and create one. The other thing I need is a function that creates those intermediate images. I need to call this guy so it creates those images for me so I can store them. Now, what does this function do? You give it the epoch number, whatever it is, and then what does it do? It comes here and it creates a subplot 5 by 5. So they're going to be 5 by 5, 25 images in a 5 by 5 arrangement. And then here we have some noise. You might say, what is this noise for? Well, remember, noise is that input to your entire channel, right? So you pass a noise to this, not channel, network, I'm sorry. You pass the noise to this network with a number of rows and columns and with that latent dimension, right? So create the noise vector and pass it to the generator with the predict. So this is going to be the output of the generator. So this image is that fake image, which right now with the current weights of the generator, after so many epochs, you get that image. And remember, these images were in range -1 to 1, right? That's what we did in the beginning. So here I bring those back to a range 0 to 1 by multiplying them by 0.5 and adding a 0.5. And then now I create the subplots with 5 rows and 5 columns, a figure and axis. Then I say for I in range of rows, for a j in range of rows, which is basically range of 5. So here I'm going over one by one of the subplots. I go to that specific subplot axis I and j dot image show of image index, right? Reshape to W and H CMap gray. What does that do? It shows that fake image that you created. It reshapes it to H and W, make sure the image is reshaped into H and W, because the size of that is H times W. Okay, the size of that. So you reshape it into a matrix instead of a vector, and make sure that image is in grayscale, not color. And you're going to show it on that specific subplot. And you turn the axis off so you don't see the ticks, the X ticks and Y ticks. And you keep going on this index. Okay, so this index should start from 0 and go to 24, so it knows which one of those images is to be shown on that axis. Now you might say, is this image, is it just one image? No. So this image is not a single fake image. This image is 25 fake images. Okay, so this guy here is what? 25 fake images. This image is a combination. It creates all of them in one go. Another way to do it is, when you create this noise, just make the dimension of that 1 and latent dimension, and then each time you pass this this one here, these two lines, you can bring them into this nested for loop. So you can do it one by one, generate them one by one, and then you didn't need this image.index. But here we generated all the 25 images ahead of time, and then we grab each and every one of them and show them on the subplot. Then once we show that image, we save that picture as gan.image.epoch ping. So it's going to be like epoch 0.ping, epoch 200, epoch 400. Remember, every 200 images, we have what? We have one saving. And then we close the PLT so it can be used next time for the image show again. So you have to release that PLT IM show. If you don't close it, you're going to have some problems. So this function is just for capturing and saving images. Now let's go to the main training loop. So here I say for epoch in the range of epochs, which is 30,000, go ahead. What would you do? First, you want to train the discriminator. So here we basically go ahead and create a random integer number, and then go to the training images, grab that index, right? So if this guy creates like 500 or 200 or something, remember we have 50,000 training images. So this guy is not going to go from image 1 to image 2 to image 3. Each time it grabs a random image from the training set, and not just one, a batch size. Okay, so it's not just going to create basically one random integer, it's going to create a batch size set of random integers, which in this case 32. So it creates 32 random integers, and then what? It goes and grabs all of those training images, and then here call them real images. These are the images for your training, these are your targets. Now it creates a noise vector, but again, this is not for one image, this is batch size and latent dimension. So this is the noise that you need to create 32 fake images, not just one. So here you're doing everything in a batch format instead of one by one. You pass those noise to the generator prediction to create the fake images for you. So again, this is what? This is 32 fake images, and here are what? These are 32 real images. And now that you have your fake images and real images, it's time to pass them to discriminator to get you what? To get you the whether it's fake or not, and give you a loss function. So how do you do it? Now you pass these real images to the discriminator, and you want it to train on batch, and then you pass it ones, then you pass the fake images and zeros. So do you see what you're doing? These real images, the discriminator should generate for them only ones, because one is for class real. And for these fake images, the discriminator should generate what? Should generate zeros, right? So I pass to it the real images and I expect ones. I pass to it the fake images and I expect what? Zeros. So I train it, and each time it will give me what? It will give me the value of the loss function and the accuracy for those real images, and next time it passed to me the loss function and the accuracy for the fake images, and then I combine or add the loss of the reals and the fakes by taking the average of them, and I do the same thing for the accuracy. I combine the accuracy on the fake and real images and again take the average. So what were these ones and zeros? These are the ideal detections, right? For real images, we needed ones, all ones, and for fakes, these are what? The zeros. So the zeros and ones are the targets. These are the labels that we really want the discriminator to give us when we are training on what? On batches. And you see the size of them is what? Batch size, right? So these are 32 ones, and we expect this guy to give us 32 ones, but it might or might not, right? So here, this is how you calculate the loss function and the accuracy for the discriminator. One more time, I need to emphasize that here we use train on batch. Okay, so this train on batch will only train your network on a single batch. That's all it does. That fit that we don't use here, that will train on one or more epochs. You can pass it as many epochs, and remember, in each epoch you have a lot of batches to train, right? In this case, you have 50,000 images and each batch is 32. So 50,000 divided by 32, you have what? You have probably 1,600 or something batches per epoch, right? Yes, so this function should be very fast because it's just one batch. That fit takes forever because it's so many epochs and each epoch has so many batches. But instead of that, we are doing it with what? We are doing it with a for loop. We are doing the same job. For discriminator, again, we create a bunch of random integers, right, with latent dimension. So this noise is going to be a multi-dimensional noise with 100 values, and not just one of that, 32 of that. So we can pass them to the combined model, train on batch, and then again the output, remember the output that we want when training the generator is all what? Ones. Remember that when we train the generator network, we want all the targets to be what? To be ones. So that's exactly what we are doing here. We get the G loss, and now we have the G loss and the D loss. We append them to what? To the D loss and G loss, and that's what we need. We really did not use this D accuracy and append it. We can if we want, right? But here the goal is just to display them, not to store them, because we just stored the loss functions here to show. But if you want, we can store what? Feel free to store this D accuracy. So you can create a D accuracy vector, and each time you append this D values to it, so later you can plot them versus epoch if you want. But here, instead of that, in this for loop, we say every 100 epochs, go ahead and show the epoch, go ahead and show the D loss, the G loss, and what? The D accuracy. And every 200 epochs, go ahead and call this function sample images. So it what? It shows the images and save the images. Do you see that? So every 100 show the results, every 200 go ahead and what? Show the save the images. And finally, when we have everything, here is those two loss functions. As I told you, you see all these oscillations, and you don't see a beautiful monotonic behavior. I told you the reason for that. And here are some of those sample 5x5 subplots that we stored. This is in the beginning. At epoch 0, you see clearly that the network started with all random noise. Then after 10,000 epochs, remember we have a total of 30,000. You see, look here, now you have numbers that are similar to the digits in MNIST. And after 29,800, which is almost the end, now you have what? The numbers generated by generator network that are very close to MNIST, okay? And now it is very hard for your discriminator to discriminate them from the original MNIST pictures, okay? So this is one way to code this GAN here. As I said, the alternative way is here. You can see it on TensorFlow website for deep GANs. And there are two ways to code the same job here. This is how it's done over here. And remember that this 30,000 epochs will take you a good time. So if you can do it on GPU, it is going to save you some run times. Hopefully this video was useful to you and you learned some basics about GANs. My goal here was not to go into all details of GANs, but I guess I gave you enough information so you understand them. Thank you so much. I'll see you in the next video.